Hello, demons. So today we're going to look at simplifying radicals. What you're going to want to have on you, some notes, a calculator, and then that goldenrod yellow card that you have of the perfect roots table. So today you're going to also want to have that little foldable out that we made. If you want to turn to the flap that's called Simplifying Radicals, that's the flap we're going to be working on today. And here you have what we're going to work on. Very first, we're going to do some examples without variables, so label the top with that, and the bottom is going to be examples with variables, assuming they are positive. So if you want to label the top and the bottom quick before you continue on in this video. So this is that perfect roots table you should have had done already. Please make sure that you have it on. You're going to really want that today. And here are the first two problems about simplifying without variables. And we've seen these before. I'm going to put a little line in the middle here. So this is number 1 and number 2 on the top area. So we have the square root of 40. We've simplified these before. So there's a little 2. So under the square root chart, we're going to want to find a number that can go into 40 evenly. So under the square root column, what's a number that can go into 40 evenly? 4. So I can have the square root of 4 and 4 times square root of 10. That will give me the square root of 40, right? So then square root of 4, we know that is 2. And square root of 10, well, we can't break that down anymore. So we know our final answer is going to be 2 square roots of 10. We've seen this one before. This is not anything new. But what about a cube root? So instead of looking in the square root column like we were doing last time, so instead of looking here, we need now to look here in the cube roots column. So I need to look, what's a cube root, one of those numbers in that column, that can go into 40. I need a number that can go into 40 evenly. And it looks like 8 will go in perfectly, right? So if I have 8 times 5 gives us 40, or 40 divided by 8, that gives us 5. Alright, so then the cube root of 8, we know that to be 2. And we can't do anything with the cube root of 5, so that's just actually going to stay there. So we're going to have 2 times the cube root of 5. That simplifies down. Numbers 3 and 4. Let's take a look at this one. So if I go kind of make myself a little scribble in the middle. Cube root of 72. Just like last time, look at your perfect roots, perfect cubes table. Let's see if we can find a number that can go into 72 evenly. Which you should find 8 will go in there perfectly. And 8 times 9 makes 72. Cube root of 8, if you look, follow the row, you should get down to 2. Cube root of 9, that doesn't fix at all. We can't solve that one at all. So that one's just going to be 2 times the cube root of 9. Fourth root of 5, 12. This one, what is a fourth root? So we're going to look at the fourth root column, and we're going to figure out what number can go into 512. Very first thing I noticed 16 can go in perfectly, and 16 times 32 goes perfectly, so I know the fourth root is 16, we know that to be 2 there. 32 though, I noticed I missed something, because 16 can go into 32 also. So let's simplify one more time here. Like that, because 16 times 2 does give you 32, right? The fourth root of 16, I know that's 2, and that should be a little 4. Little 4, there we go. And then the fourth root of 2. Can't simplify at all. Let's multiply these two guys together, because they're both sitting on the outside. So 2 times 2, that's 4. And then I'm going to have 4th root of 2. 4 times the 4th root of 2. Now, you could have taken out a 81. That would have worked perfectly right away. Then you would have not have had to simplify double time. Usually, it's best to either A, simplify to the biggest number, or if you do simplify with smaller numbers, double check, make sure the one you didn't simplify can't simplify further. Now to the bottom part, simplifying with variables. Here's number 1 and number 2. Best thing I agree with is start with the numbers. So let's break these into 2 separate radicals. So we're going to have the number radical, 4th root of 625, and the 4th root of x to the 4th. Let's look over here. The 4th root of 625. So let's look under the 4th root column and at the 625 and look to the left. 4th root of 625. Oh, that should be 5. That one's a perfect one. Comes out perfectly. Now, if you remember back from when we would do x squared and we would square root and now get rid of the squared. Well, that works for every single one. So the 4th root of 4, x to the 4th, that's actually going to cancel out the 4th root and the power. So we're going to be left with just x. So our answer here would be 5x. Let's look at the next one. Just like last time, let's break this into 2 separate radicals. There we go. 3rd root of 64, if you look on your chart, you should see that that is equal to 4. Now, notice how the index does not match the exponent, so we can't just cancel them out. But is there a way to uniquely write y to the 6th so that I have some 3's in there? Well, I know y to the 6th is just y to the 3rd times y to the 3rd, right? Because you just add exponents. So what if I make those under some radicals? Looks legal, right? We could do that. So then y to the 3rd cube root, that's going to erase those. So I'm going to be left with a y there. Same thing here. Be left with a y there. So I have a y times a y. It's going to give me a y squared. So it looks like I have 4y squared out of that problem. That's going to be my answer there. Alright, let's look at numbers 3 and 4 here. So just like last time, let's break each of them into their own little radicals. There we go. 5th root of 4, that can't simplify, so he's just going to kind of sit there and wait until we're done with everybody. So now the radical or the exponent and the index don't match on this one. So I need to uniquely and strategically write a to the 10th so I can somehow get some 5's in there. So what if I would write the inside as a to the 5th times a to the 5th? Because 5 plus 5, that gives me 10. So then I can write them both under radicals, which gives me the ability to get rid of it. So I get a times a, which we know, a squared. B to the 6th with a 5th root. That's not going to really help us. So what I'm going to do is I'm going to uniquely write b to the 6th in the inside. I'm going to write that as b to the 5th times b to the 1st, because 5 plus 1 gives me 6. It's going to get rid of that. I'm going to get a b. That's just going to kind of stay in there. So now, let's look here. Who's on the outside of the radical and who's still on the inside? I have an a squared on the outside. I have a b on the outside. And then I have these two guys right here on the inside. These two guys right there. So let's write my radical. Little 5 on the outside. Whoops. Little 5. There we go. I have a 4 on the inside and a b. That would be my final answer for that one. So now I'm going to show you a little less work on this one, just to show you kind of my thought process, but not the rest of it, not all the work. So square root of 40, remember there's a little 2 sitting there. So let's break it into its 2 parts. Square root of 40, we did that earlier. Let's take a look here. We know the 4th root of 20, that was 2 square roots of 5. It should be the very first problem we did, 2 square roots of 5. Now, I'm going to think the square root of x to the 5th. I'm going to think, how many groups of 2 can I make on the inside here? I can make 2 groups of 2 with 1 x left over, right? So I would have 2 groups of 2, so I would get an x squared, 2 groups of x's, x squared, kind of makes sense, right? And I have 1 x left inside of that radical. Whoops, that should be an x, not a 5. Silly, silly. That should just be an x. So now I'm going to combine what's outside and what's inside. So 2x squared looks like he's sitting on the outside. And I have 5x on the inside. And that is the end of that problem. The best way I can see it is group x's together. Think of how many groups can make a number, and then what are you going to have left after you make some groups. That's the end of the video. See you later.